Hello, everyone. I'm Shalini Dubey, Marketing Manager at Element Materials Technology, and I would like to welcome you and thank you for joining us today. We are going to wait for a couple of minutes to get started so everyone has the chance to join. So let's wait for a minute or so. So the numbers are continuously increasing, and I think we can start now to respect the timing. So once again, I would like to welcome you all in today's webinar, which is on point source emission testing, continuous emission monitoring systems, PEMS, and relative accuracy test audit, which is brought to you by Element Materials Technology. But before we get started, I would like to cover a few housekeeping items where if you have any questions throughout the webinar, you may submit them on the right side of your screen, and we will address as many as possible during our Q&A session at the end of the webinar. If there are any questions we are unable to get to, we will make sure that we are following up with you after the webinar, and you will definitely get answers to your questions. Today's presentation is being recorded, and the link to the recording will be available on element.com and emailed to all the registrants. After the webinar, there will be a short survey asking for your feedback, and we would greatly be appreciative if you take the time to share your thoughts. And finally, if there are any technical challenges with GoToWebinars, because there have been reports to GoToWebinar freezing or losing audio going in the past. So if the webinar seems to be freeze on you, our first recommendation for troubleshooting is to try refreshing your browser. Next slide, Alex, please. And before moving on to today's webinar, I would like to briefly introduce Elements for those who don't know yet. We are one of the largest independent providers of materials, environmental, and product testing services in the world. Element is the best and most trusted testing partner, providing high value, critical services to the aerospace, transportation, energy, environment, fire and building products, and connected technology sectors, where failure is not an option. Our purpose is a simple one. We make certain that all of the materials, products, and devices that we test, inspect, and certify are safe, fit for purpose, and compliant with all relevant industry standards and regulation. Together, we help our clients to develop better products, improve time to market, and help our customers become more efficient through the collective experience and knowledge of our team, which is over 7,000 engaged experts across the globe, where we are working together to make a safer tomorrow than today. Next slide, please. As you already know me, I'm Shalini, and now it's my pleasure to introduce you to our presenter today, who's Mr. Alexander Hardy. We call him Alex Hardy. And so Mr. Hardy is the Technical Director at Element Materials Technology for Environmental Middle East and Asia Pacific region. Alex has obtained his master's degree in public health and environmental engineering and has more than 2 decades of experience in supporting and consulting our customers across the globe, from chemistry as well as environmental fields. And now, without any further ado, I would like to hand it over to Alex to take this forward. Over to you, Alex.
Thank you very much, Shalini. And good afternoon and good morning to you all from me as well. If I could say at this stage, I do have a little bit of a cough, so I will try and keep that under control. So if I do cough occasionally, then forgive me. But we shall move straight on with this. To give you an idea of what we're going through, time is quite tight. It's a very large subject, so we're just having a brief look at each one of these things. But if anything particular comes to your attention, as Shalini said, please go through the correct procedure to raise a question, and we can answer that at the end of this presentation. So very briefly, we'll just have a quick introduction to point source emission testing. What is it? Just a single slide will talk about health and safety. It's incredibly important to us and to all, doing stack emission monitoring can be a particularly hazardous operation, so it's worth bearing that in mind. A bit about the test methodology, sampling, monitoring, and as Shalini said, we will have a look at continuous emissions monitoring systems, CEMS, a bit more about RATA, which is used to test the accuracy of these systems, and finish on a bit more up-to-date type of information on the way things are going forward with Predictive Emissions Monitoring Systems, PEMS. And at the end of that, there'll be an opportunity for some questions and answers. So please feel free to do so. And that'll be an open discussion. So hopefully we can get some lively conversation going. Just as I said, health and safety, incredibly important to us. I am not going to go through all of this slide because it's very detailed and we could have an entire presentation on health and safety, but this is not that presentation. But just to note, as I said, stack testing is an inherently hazardous operation. If you have a look at the potential hazards there, working at height, working with chemicals, working in heat, certainly in our area of the world, environmental conditions can play a big part. We've been in situations where we're outside at the top of a warm stack, 50-degree ambient temperature, working temperature of nearly 70 degrees. So there's quite a lot of hazards that need to be associated. The gases we use can be toxic. So all of this has to be borne in mind prior to making any plans to launch a stack testing or RATA project. And as I said, we've said there, prior to every project, we carry out a site-specific risk assessment that will be discussed between ourselves and the client, and all procedures put in place to ensure that both our personnel and your personnel are operating safely. So that's important, and we can move on to the actual point source emission. I think as this seminar is titled Point Source Emission Testing, amongst other things, it might be quite useful to actually know what a point source is. And these definitions are taken from various organisations, including the US EPA and the UK Source Testing Association. A point source is a pollution in a single identified source of air. We are talking a single location. It is called a point source because it can be modelled as a single point source for mathematical modelling purposes. It can be a chimney, a stack, a generator, a large stationary vehicle. These are all defined as point sources rather than something like a road or I've said here forest fire. Roads are taken as line sources, much more difficult to model or source volumes. But we are talking here particularly, as I said, about the classical stacks that we see in power stations, etc. So that's what's known. The correct terminology, as I've said, is point source emission, but you and I and everyone in the business calls it stack testing. So that's perhaps what I will use going forward, and the terminology are both interchangeable. So we now know, hopefully, what a point source is. Where do we find them? We have a nice photograph there that it clearly indicates what a point source in this case may be. A stack. External combustion boilers, power stations, all of these combustion engines, various industrial processes. Again, in our part of the world, a lot of petrochemical plants, refinery plants, desalination plants, all that are using power that will actually put emissions into the atmosphere. In some larger organizations, cooling towers are also classed as point sources as well, and are subject to various testing requirements. So you can see there's a lot: waste disposal, incinerators. There's a great range of industrial sources and manufacturing sources that could be classed as point sources that come under various regulations depending on what country you happen to be listening from at the moment. So what is point source emission testing? There's three different ways. I mean, what we are involved in is measuring, as you could see in that previous slide, the emissions from these point sources or these stacks. There are three main ways of doing that. Initially, the sort of historic way is by periodic measuring. Simply, we are asked to go out, we take appropriate instrumentation with us, and quite simply, as we'll see later, measure the gases or the particulates within that stack that on a periodic basis, perhaps quarterly, 6 monthly, annually, they can then provide that information to the plant operators, who can calculate their total emissions and provide that to the regulators. This is done where neither of the two more up-to-date systems are in existence. Continuous monitoring, emissions monitoring systems, CEMS, are automated systems where effectively they have what we have, but installed into the stacks. So they are continuously monitoring the emissions in real time. That allows them to make any process adjustments, etc. Clearly, a lot more regulation is pushing down this route. It's fine for us to do periodic measurements, maybe once a year, and if it fails for the emission values, then perhaps that particular organisation has been polluting the local atmosphere, for the last year. So there is more and more a move towards continuous monitoring systems. And finally, the third system there is what's known as a predictive emissions monitoring system, where we are using software-based solutions to calculate real-time data. It doesn't actually do monitoring, but the software is modeled via a number of different routes that we'll see, either by real-time monitoring or by other various predictive modeling from existing systems elsewhere. At the moment, what we're going to talk about is the initial periodic monitoring, going out with equipment and measuring these stacks. Why do we do it? Well, that's a good question. Primarily, its environmental monitoring is performed principally to ensure that the plant operators, whether that be power stations or people operating generators on a building site, are complying with the current environmental legislation, and perhaps any discharge consents that these organisations may have. The larger plants will be provided with discharge emission values by their local regulator, and this is a way of ensuring that they are conforming to that. Again, that data, as I said, is used for emissions inventory compilations that get handed in maybe on an annual basis to the regulator. We also perform emissions monitoring to ensure that PEMS and CEMS actually work. It's not good enough to say I've installed a CEMS, I continually monitor my own emissions. You have to be able to prove to the regulator that that those systems work. So we go out and use the old-fashioned periodic monitoring to check that the new continuous monitoring systems actually work. Again, there's some other information there. Process efficiency is a big area in plants, that you can monitor how efficient your process is, and then make adjustments to improve that. Emissions trading limit, it's not so much important out in the Middle East, but is highly significant in places like the US. So kind of move on a little bit to actually how this is done. There are in the Middle East, very much so, a lot of this type of monitoring and a lot of environmental monitoring in general. The regulations and current procedures follow quite closely US Environmental Protection Agency methods and procedures as well. So this is not different at all in the stack emission monitoring field, where most of the methodologies out here that are defined by regulators or even plant operators are based on US EPA. So in a lot of cases here, I'll talk about US EPA methods, but we also test occasionally to UK and EU methodologies as well. But going back to the US EPA, they operate two different tiers of monitoring methods, for want of a better phrase. One which is called promulgated US EPA methods, which are of a higher standard. They're the only methods that are accepted by regulators for compliance purposes generally. They're more stringent. They involve much more calibrations on site, a lot more monitoring. They specify techniques and performance, not necessarily methods. So just a couple of examples there. US EPA method 7E for nitrous oxides using chemiluminescence or total particulates. Method 5, there's method 15, isokinetic sampling. But the US EPA also have a secondary level of monitoring methodologies called conditional test methods, which are far less stringent, CTM 30. These are generally used for process control, used by the plants themselves. They're much simpler to do. It's a one instrument measures everything. Doesn't require the same level of calibration or, for that matter, training, but it is a very useful tool for routine, monthly, weekly, even daily monitoring of your systems to check that they are in accordance of where they should be. So that's the sort of two levels that are required. Clearly, Element provide both of those type of measurement methodologies, depending on what's fit for purpose at the time. If we consider the standard reference methods, which is the same as the promulgated methods, they are referred to as standard. These are generally split into two different techniques. Direct reading instrumental techniques, which is used for gases, and then we're looking at isokinetic or non-isokinetic multi-phase monitoring, which is more difficult, and it's used for things like particulates, dioxins, metals, etc. So there are two completely different types of standard reference methods that are used. Again, I'm not going to go through all of this, just to give you an idea that if we're doing direct instrumental methods, that covers things like CO, NOx, SO2, etc. Principally all of the gases. We also do VOCs using FID by US EPA method 25A. A couple of photographs there that give you an idea of what's involved. these very large stacks, and certainly, as you can imagine, again, in this part of the world, we are involved in going out and monitoring these on site. Our instruments have to be incredibly well calibrated. They're incredibly sensitive. So we have to house these instruments in what is essentially a small mobile laboratory at the bottom of the stack. As you can see from those photographs, we have an air-conditioned, temperature-controlled, humidity-controlled laboratory that holds all our instrumentation. And the gases are essentially transported from the sampling ports within the stack to the temperature-controlled portable mobile laboratory. That's incredibly important, especially in this area, because significant changes in ambient temperature will make significant adjustments to the performance of our instruments. And clearly, we've got to ensure that our instruments are correct if we are using them to verify the accuracy of third-party instruments. So that gives you a little rough idea of what we would be doing and how we do it, and what you would see if Element came to visit you to do some stack monitoring on your stack. A lot of different equipment we use. These instruments, as I said, they're all housed in our mobile laboratory, and they are portable CEMS, portable continuous emissions monitoring systems. That's what we use, as I said, to check either the periodic emissions or to check the accuracies of CEMS or PEMS. Clearly, there is an issue that we've got to check that we've got to make sure that what we do is correct before we can we can tell someone else that they're not. So, but we will come to that. The other method I talked about is conditional testing methods. It's a much simpler idea. It's a one instrument technique. The previous instrument there, or previous techniques you saw using the standard reference methods, we have different techniques, as you saw, for oxygen, for CO, for NOx, for VOCs. They are all completely separate instrumentations at different techniques, whereas in conditional test methods, CTM 30, we have a single instrument operating on chemical performance and the chemical sensors that can cover all of those gases. Clearly, they're not as accurate, but there is certainly a place for these instruments, principally, as I said, for plant operators. Much more simple to use, much quicker, and can give an indication of emissions concentration that would be very useful to let plant operators know that they are either, within their consents or not. And as I said, we're happy to do both, and there are certainly situations where both are very useful. The other thing I talked about was isokinetic sampling, as you saw there before. The portable CEMS instruments that we use are essentially for gases. When we look at other materials that require to be tested isokinetically, we are talking about particulates here. Now, the gases before, as I said, we take the gases direct from the stack, direct through heated lines to ensure there's no condensation and loss into our portable lab, and then the instruments will then do direct reading analysis. In isokinetic sampling, that's not possible. We need to do abstractive sampling, where we take a sample of the gas out at stack height via a number of techniques that we'll show you, and we then use this that will be followed generally by analysis in a laboratory. So that this isokinetic sampling does produce various either liquid samples, particulate samples, etc., that are sampled in a lab. So typical, as I said, emissions there, gravimetric analysis purely for dust or PM10, PM2.5, or we're looking for gaseous solids and dioxins, metals, PAHs. Again, if we're looking for anything where droplets are formed, Then we've got to sample isokinetically. That'll cover a lot of acid gases, sort of HCl, HF. SO2 can be a problem if it's wet, because you'll produce SO3 and SO4. So you can't do the gaseous technique. You need to use isokinetic techniques. So again, these are all things that we're very happy to discuss at any time. Every stack testing project requires a fair amount of early discussions on not only the health and safety issues, but actually on what sort of parameters we need to be measured, at what concentrations, and how best to do it. So there's a lot of pre-site work that needs to go in place before, to ensure that what we do is correct, and we give you what you need and what the regulator is looking for. Just a little picture of a standard isokinetic sampling unit, which has to go to the stack, the top of the stack, or a platform on the stack. This unit altogether, 75 to 100 kilos. Now, we've got to make sure that we can safely get that to the top of a stack. We've got to safely ensure that we can operate it there. So all of these things need to be taken into consideration. But, a nice little picture there of how it's done. And you can see number 4 is the umbilical cord. Very important. We are sometimes subtracting gases at very high temperatures. We cannot allow those gases to condense prior to when we want them to condense. So, things are normally transferred in heated lines and umbilical cords to make sure that the gas stays, or any material within that gas stays gaseous and doesn't condense out. Just very briefly, again, we've had a look at the equipment, but what does isokinetic mean? What are we really doing here? Well, I think we've got it there. Iso meaning equal, and kinetic meaning move. It's not as easy as one thinks to stick a probe into a vent in a stack and sample easily. Because the stack walls, the diameters, anything within that stack will cause turbulence. This is not such an issue when you are monitoring gases, because it's simply moving them around, but it is a very significant issue when you're looking for particulates or you're sampling. So isokinetically means that we are abstracting the gas from the stack at the same rate and in the same direction that the gas is moving within that stack. If you can't do this, then your results are going to be completely meaningless. So it's very, very important that we look at that. As I said, how do we do it? We've got to get this representative sample, because, as I said, the initial effects of gravity, the different materials within the stack, the shape, the dimensions of the stacks, any bends, anything like this means that there's turbulence. So we have to make allowances for that. I'll just briefly run over these. Again, it's just to give you an idea that it isn't quite as simple as going and sticking a probe into a vent. There's a lot goes into it. If you can have a look at this, the way that we ensure that we get isokinetic sampling is by doing on various sampling points across the particular stack. All of this is defined in US EPA Method 1, but again, you can just get an idea here of the number of potential sampling points that we would need to do in a single stack. So it's a multi sampling operation when you're looking at isokinetic sampling. That's a pretty traditional circular cylindrical stack. Occasionally we get rectangular, not exactly stacks, but ducts. Then again, it's very important that we are doing multiple sampling in various defined locations so that we can calculate that we are we are taking an isokinetic sample to ensure that the results that we produce are valid. Again, all of this sort of stuff has to be looked at prior to any major stack emission monitoring program. We'd be coming out, we'd be looking at those stacks, we'd be making sure that everything is there that we need. So you can have a look here, the requirements. The sample location is far downstream of disturbances which could easily change the flow. You know, we're not looking at taking samples of stacks are 10 meters high. You know, we're not taking samples at the bend, at the bottom of the stack, or within a meter or two of that. Again, all of these, as I said, are defined in US EPA method 1, but we need to be we need to examine these stacks to make sure that we can meet these criteria. A very important criteria is the minimum diameter sampling port. Often we will go out and people will ask us to do, let's just say, particulates, which needs to be done on isokinetically. The sampling probe that we use, the sampling head and filters that go into the stack require generally a 4-inch diameter sampling port, and quite often that's not there. So we either have to change the techniques and make a comment to that effect in our reports that we did not follow the reference method, or for that matter, the plant operator will have to make some adjustments to their particular sampling ports to allow us to do the sampling in accordance with the reference methods. As you know, as I'm saying before, you can gather there's a lot of discussions goes on prior to doing these operations. A working platform, we've said there, we've got a lot of equipment to take up to the sampling areas on these stacks. We need to make sure that we can get them there, whether there's lifting lugs, that they're safe, that we've got adequate room on the platforms, and that they're protected with rails, handrails, etc. All of these things need to be looked at. These are just some schematics of an isokinetic sampling platform. You know, some of these probes on these very large stacks, the probes can be 3 meters long. You know, we can't operate on a 1 meter wide platform with a 3 meter long probe. It's just unsafe. So again, we look at all of these things and try and advise our clients the best way and the safest way to allow us to do this work. And as we've said there, for larger stacks, it's advisable that 4 sampling reports are required so that we can do sampling at 90-degree angles, rather than have 2 sampling ports at 90, where we're having to use much larger probes to effectively traverse the whole diameter of the stack. Anything's possible, but you know, these are all things that we need to take into consideration before we do this. Again, just another look at what we do, and you can actually see it, see what we're doing there in practice. Just finally on this a little bit, I alluded at the very beginning to health and safety because it's clearly the most important thing that that we are concerned with when we go out stack monitoring. But there's some just breakdown of some of the more obvious hazards associated with this type of work. Fall prevention. Sometimes some of these stacks are 60, 70 meters high. We've been on these things where they say they've got a handrail, and the handrail happens to be 400 mil off the ground. It's not a handrail, it's a trip hazard. So these sort of things we need to look at. Harnesses, power supply. We need power supply to run our equipment, so that needs to be there. Again, as I mentioned before, any lifting equipment, any hoists or any lugs that happen to be on the stacks, we need to ensure that they have been load tested and are safe to use. And we've got all the other things there, gases that we work with, etc. So again, all of this forms part of any pre-start work. And that was a quick run through of stack testing. As I said, it is brief, but we're happy to discuss any of these things in more detail, without a doubt. More and more, as I've said, and certainly even in this region, the major organisations, the ADNOCs, the Aramcos of this world, Qatar Gas, are now either being asked or voluntarily introducing what's known as CEMS, Continuous Emissions Monitoring Systems. I mean, what these things are, as I said, is essentially what we do with various sampling probes installed into the stack, but abstracting the gases in real time that will then take them down to an analyzer station at the bottom of each stack. They're commonly used to continuously record, report emissions data as a means of process control as well, very important, and to comply with emission standards. More and more, again, in this area, if you take the Environment Agency in Abu Dhabi, if you take what is NCEC, which was GAMIP in Saudi, they're beginning to ask these big process operators not only to install CEMS, but to make sure that give them, the regulators, access in real time to the output from these CEMS, so they can actually sit in their offices hundreds of kilometers away and dial up and check the emissions output from hundreds of point sources around the country. So, you know, it is a case of Big Brother watching you, and that's great. It's good for environment. It's also good for the organisations and process control. They're looking at that, and it's making them actually or use this data. Again, in terms of the routine CEMS, it covers most of the simple stuff, as we've said, NOx, NOx, sulfur dioxide, CO2, quite often again for process control, oxygen, particulates. And that's a little schematic of how it is. The actual photograph there shows the sampling probes. The schematic shows where it's down. The CEMS analyzer boxes there that are shown in green normally sit at the bottom of that stack. They will then go into a data logger. That data logger then will then send that data to a process control on the plant, but as I said, can also be requested to send that data directly to regulators. It's yeah, as I said, the continuous CEMS are probably, you know, they've been around for quite a lot of years, but more and more their use is being mandated. And that's fine, but we've got to, you know, as I said, it's not good enough to say we've installed the CEMS, we're okay now, we don't need to do anything. Clearly, you have to prove that that CEMS actually works before the regulator will accept data from that CEMS in terms of proof of compliance. And not only do you have to prove that that CEMS works, you have to prove that it continues to work over some time. So what that requires is some periodic evaluations of the CEMS. This includes calibrations on a daily basis. Internally, we don't do this. This is plant operators, interference tests, flow monitors, and perhaps quarterly or annually looking at what is RAA or RATA testing. That may be a requirement. In terms of all ongoing performance testing and initial testing, there are two distinct US EPA regulations, both US EPA CFR 40, but one's Part 60 and one's Part 75. In terms of our experience in the Middle East, most work is done under Part 60, which is less stringent, but more and more we're being asked to look at testing in accordance with CFR 40 Part 75. But as I said, what is the difference there between them? There you go. Part 60 provides a requirement on emission limits and applied generally when complying against milligram per cubic meter reference values. Different process sectors. Again, I'm not going to go through this, but happy one day to go in a bit more detail about CFR 40 Part 60 or Part 75 if people are interested. But these standards provide performance criteria data, performance specifications as they're known, on for various gases, what deems to be acceptable in terms of the performance of your CEMS. They are different for Part 60 and Part 75. As I've said there, Part 75 is generally more stringent, are used measurements in trading schemes. If you're doing emissions trading, which I'm not aware of there is any significant amount at all in the Middle East, it is only acceptable to do that if your emissions are monitored under Part 75, as the criteria for that are significantly more stringent than Part 60. So, but both of these, Part 60 and 75, define a series of CEMS verification tests, i.e. is your CEMS working, including what is known as RATA, a Relative Accuracy Test Audit. That's part of our heading on this. So what is a Relative Accuracy Test Audit? Well, quite simply, it is used to compare the accuracy of a CEMS, or I have said PEMS, but we'll come to PEMS, but it is a very similar process for PEMS, to data collected simultaneously by a third party, such as ourselves, that is using a portable CEMS data. Clearly, there has to be comparison or appropriate comparison between those data to prove that your CEMS works. Again, I'm not looking too much. I'll bring a slide up in a little while that tells you the variance that's allowed, but you know, you can go through this. As Shalini said, this will be on our website, and you are more than happy to, or more than welcome to download and go through in your own time. But essentially, this RATA testing is there to prove that the accuracy of your CEMS or PEMS meets the accuracy requirements stated under the performance specifications of Part 60 or Part 75. This is what we do. We go out with our mobile lab to collect data, to compare that data against the produced data from the CEMS. So when do you do relative accuracy test audits? It's required by regulators to ensure the accuracy of CEMS or PEMS. Again, very much so before installations can be handed over. It's also required by people who are buying the CEMS or PEMS. If you're paying, you know, millions and millions of dirhams or reals or whatever to install PEMS, or purchase PEMS and have them installed by a supplier, you certainly want to know that what they've sold you works. So again, as part of the installation process, there is usually a handover criteria, which again would require third-party testing to prove the accuracy of the PEMS or the CEMS. Again, we should look at it on an ongoing basis. Again, there may be local requirements to do this as a third party. If you look at the US EPA, they would state that as a minimum, are required to do third-party RATA testing on CEMS is required to do at least annually. This, you know, clearly, as I said, you can't install a system that monitors emissions and never look at it again and believe what it says, because things do go wrong. And you know, there is a requirement that these systems are third-party checked on an annual basis at least. Again, I'm not going to waste too much time on this. It's worth saying that if you're doing at the end, if you're doing relative accuracy test audits, you must use conditional test methods. They're the standard reference methods. The use of conditional test methods are not permitted for CEMS RATA testing or PEMS RATA testing. Again, we've said some of that stuff before about the number of, you know, the locations that we require. Sampling facilities must enable us to be able to get the samples correctly, the right number of sampling ports and locations like that. So there are a few specific requests there. Again, how do we actually do it? This can get a little bit tedious, I have to say, but we carry out a minimum of 3 sets of reference test procedures at three locations within each duct while it's operating at least a 50% load. So we're talking about a minimum of 9 sets. That is then compared with the continuous data that we get out from the CEMS, and we make statistical comparisons of our data against the CEMS data. And then a fairly obvious question, how do we know, or how do you know that the CEMS has passed? So again, looking at those performance specifications in US EPA CFR 40, there are various tolerances allowed, because clearly we will be getting some differences using 2 different measuring instruments. So, but there are tolerances in those differences. If you look at the relative accuracy of O2 and CEMS, must be no greater than 1%. So all of these we will work out on a statistical basis and be able to provide a fully detailed report to say whether that CEMS has passed and is fit for purpose or has not. As I said, just a quick summary. Going forward, there are different criteria for Part 60 and Part 75. In both the initial requirements, which is on the left, if you're installing CEMS, the types of tests that are required, and the acceptance criteria. But going forward, and this is really important, and I do have to say, in the Middle East, that this is quite well, arbitrarily at times, but it's getting much better. Primarily before, people were forced to install CEMS into them, and the continuous, shall we say, checking or maintenance or calibration of those CEMS was sporadic. But it is becoming much better now. There's much more enforcement. There's much more social responsibility from the large process operators. So they are now following, as I said, on the left is the tests that need to be done in installation, and on the right is the tests that should be done on an ongoing basis, depending whether you're looking at Part 60 or Part 75. I won't go through them, but I think it is worth looking at on the right-hand side, just the frequency that you can see. CEMS operators should be daily subjecting their CEMS to calibration drift, and then quarterly and annually in terms of relative accuracy audits or cylinder gas audits or third-party RATA testing, and these should be carried out by third parties. So again, it isn't install them and forget about it. There should be in place an ongoing monitoring regime, both internally and by using external third-party accredited organisations. So we're just running through now, and I'll have a quick run at a quick chat on PEMS. This is, as I've said, what are PEMS? Predictive Emissions Monitoring Systems are software-based solutions able to deliver reliable real-time data emission estimations. I use that word, exploiting advanced mathematical or statistical models. As I said, there is no actual monitoring goes on with PEMS. It is all done statistically, mathematically using software. The government regulations require gas turbines to continually measure. So again, there are 3 allowed ways: manual measurement, CEMS, model-based PEMS, or statistically based PEMS. There are 2 different types of PEMS modeling. It is becoming more common at the moment, PEMS, and you'll see why later, but it's relatively new in this area. We only began to monitor PEMS perhaps 3 or 4 years ago. They are still quite not rare, but more frequently it's much more common to have CEMS systems. But more and more, the process regulators, the operators, are moving towards PEMS rather than CEMS. And again, we can have a look and see why that is. As I said, there are a couple of approaches to PEMS. There's a model-based PEMS or a statistical-based PEMS. But as I said, instead of actually sampling the gases, PEMS does calculations, statistical calculations, computations based on the feed parameters that go into the process. Turbine temperatures, pressures, speeds, fuel type, ambient temperatures, humidity, etc. All of this is fed into a quite sophisticated thermodynamic model, and on the basis of that, it continuously monitors operation parameters and feed parameters and continuously adjusts the calculation to predict the emissions output that's coming at the time. As I said, model-based PEMS utilize modeling techniques. The employee first, well, I won't go into it all, but the employee sort of kinetic reaction-based statistics that will then compute the potential output from the input material. Or you can use statistically based approach where they have collected large amounts of data from similar operations before. Out here, most of the stuff we've been doing are model-based. Almost everything we've been working on is model-based, where we will actually, during the model building of the PEMS, we will be on site collecting emissions data for sometimes weeks, to be honest. Normally, perhaps a week or two, but we've been on plants in Abu Dhabi for 3 and 4 weeks at a time, where we're collecting continuous data of emissions output. That is then being used to combine with the continuous data of input parameters and operational parameters to essentially refine a model that can then make the predictions. But again, it's back to what I said. PEMS are no different to CEMS. You can't install a PEMS and say to the regulators or everybody, it's okay, we've got a PEMS in place. It's giving us a printout, telling us what might be going on. It all looks great. Goodbye. We don't need to do anything. Clearly, models need to be checked. The whole system needs to be checked as well. And as I said there, in terms of calibration of PEMS, even if someone is using a statistical model PEMS, you know, they will install of the software and everything into the plant, and we then go out, do some limited amount of monitoring, which will allow them to fine tune and calibrate that. But again, PEMS is the same as CEMS in terms of the requirements under US EPA, that you should be looking at relative accuracy audits on a quarterly basis. RATA should be carried out annually. Now, you know, this is important. Please don't think that we can stop using this. In that respect, once they're installed, PEMS and CEMS are the same. There is a requirement to make sure that you are providing ongoing calibration status checks up to satisfy the requirements of the regulator. Again, I'm not going to get into this, but this is how it's done. Again, it's quite simple. PEMS are a little bit different. You have to do 3 different loads because clearly the model has to be shown to work, or the predictive model has to be shown to work at all plant operating processes. So it does require different levels of initial monitoring and testing. As you can see, high, low, and medium loading. And we also need to look at quarterly RAA and annual RATA. The RAA, according to the US EPA, assuming in your first year everything seems to be working very well and you can prove that, for PEMS you can reduce, you don't need to do quarterly, you can reduce that to 6 monthly. But again, on the basis that you've done a year or two's worth of monitoring and everything has shown to be fine. Finally, I'll just have a quick run through this. what's the difference between, well, what's the advantages between CEMS and PEMS, and why are people moving over to PEMS rather than CEMS at the moment? It's worth mentioning. As I said, what's the advantages of a CEMS? CEMS provide continuous measurement of emissions, direct measurements. They are directly, they have probes, they have measurement instrumentations in the stack. They are giving direct readings of real-time data that is being emitted. And at the moment, CEMS data is more widely accepted. It's actually more accurate as well because it's real-time data. So it's more widely accepted by regulators and governments across the globe. That is slowly beginning to change. Clearly, even in this, this part of the world, we're well aware that the regulators in UAE and Saudi, Qatar, etc., are moving towards PEMS slowly, perhaps, but they are moving towards there. They are becoming convinced that perhaps PEMS are acceptable, but there's some way to go. And it's purely on the fact that, as I said, CEMS give actual true direct readings, whereas PEMS give predicted readings, calculated. But again, there are some advantages to PEMS. PEMS can be significantly less expensive than CEMS. As I've said, they are typically 20 to 40% of the cost of CEMS. But one of the reasons that they can be much cheaper is that PEMS can be used to monitor. I apologise for that word. Can be used to predict the emissions of multiple stacks, whereas CEMS are generally one CEMS system more or less to one stack. So if you have a multiple system, you can get away with installing one PEMS system as opposed to multiple stacks. Clearly, that reduces cost quite significantly. Again, one of the other advantages of PEMS, as I said, you're not actually monitoring anything. You're not putting anything into the stack. There's no hardware involved that requires, major changes to stack geometry or ports or anything like that. Again, there's no hardware to calibrate. And as I said, single CEMS can be configured to monitor multiple turbines. One of the other advantages, certainly again in this area, is that because we're not taking huge amounts of equipment out anywhere, we can use PEMS on peripheral, far away external locations, such as offshore, where small stacks on offshore platforms would be very difficult to mount PEMS because of the logistical and even physical difficulties. You can include these in CEMS, in PEMS monitoring. So you can understand why there's a movement towards PEMS, certainly even in this area. And I think hopefully that's taken you through where we are. It was brief, but there's a lot of information there. And now I'm very happy to join with my colleague Andrew Palliser, who will be here as well with me to answer any questions. So I'll hand it back to Shalini, and thank you very much.
Thanks, Alex, for the detailed presentation. And now is the time to take few questions. And my first question is, can you briefly explain again the differences between the two testing methodologies for routine stack testing and when each should be or can be used?
Yeah, certainly. As I said, in terms of the US EPA, there are two different methodologies or types of methodologies. Promulgated methods, which are much stricter, they must be used for RATA testing. They are used again in performance measurements, etc. They're much stricter. They are determined on techniques and performance of those techniques, not individual methods. We use them when we're checking installation of equipment, when we're doing performance monitoring, compliance monitoring, and RATA. But there is a much simpler method of doing things called conditional test methods that requires only one single instrument that works on the basis of chemical detection. And you can use them routinely. They're normally used by the process operators themselves. It's very simple to operate. Put a probe into the stack, you get multiple readings at the same time. So there are places for each of these things. Certainly in terms of regulatory compliance, you need to use the promulgated, more stringent methods, but for process control, for your own internal monitoring, then conditional methods are perfectly acceptable.
All right. And since we are talking a lot about CEMS and PEMS, you mentioned that CEMS and PEMS should be subject to external third-party checks, such as RATA, on an annual basis. So what is your experience of this in the Middle East market?
Well, mixed, I think, to say that to be at best, Shalini. It is becoming more stringent. All of this monitoring is only complied with if the regulations are enforced. A lot of larger organizations now are taking this on in terms of their own corporate social responsibility, in terms of their own requirements to meet green standards. So it's becoming more common, but certainly in previous years, our experience has been that what will happen is a CEMS or a PEMS is installed. We go out, we do the third-party verification of that, the RATA testing, sign it off as fully working, and then more often than not, we never ever hear from them again. And years go by.
Mm-hmm.
But more and more now, the regulators and the large process operators themselves are deciding that we should be conforming to the standards. So we're beginning to see more regular monitoring of these systems. It's a long way to go, but it is certainly heading in the right direction.
So from Element Materials Technologies point of view, so when Element is going out to monitoring these routine stack emissions, or for that matter, the accuracy of CEMS, how do you know that your equipment at Element is accurate to bring the perfect result?
Well, that is a particularly good question. I think I raised that a couple of times. I mean, clearly there is no point in us going out telling someone that they're either not meeting their discharge consents or their CEMS or PEMS aren't working accurately if we can't prove that that's the case. Yeah, I mean, all of our methods when we're doing and stuff like PEMS and CEMS or RATA testing, we would use promulgated methods. Our equipment is highly calibrated. The gases are all traceable, calibrated to NIST standards. All of our labs that do this work, we are internationally accredited, the labs themselves, to 17025 accreditation. In a lot of individual countries like Saudi, to do this work, 17025 accreditation is simply a starting point. You then need further approvals and auditing from separate bodies such as NCEC, the Royal Commission, or from the MOE or MME in Qatar. So there's a whole layer of monitoring that goes on that people monitor us both internally in terms of our calibrations, in terms of our equipment and accuracy, the gases, the equipment that we use. We ourselves are subject to numerous accreditation body and government and local authority auditing to ensure that what we do is accurate. And that's really important, that if you're employing a third party organization to do this, that they have the appropriate ISO 17025 accreditation and the either international or local government authority to do this work.
All right. And actually, you have already answered, or I would say partially answered the last question from today's webinar. So it was more on what approvals or accreditations are required for a third party like Element to perform this work. So if you have some more lights to throw on this.
Yeah, well, yeah, clearly, as I said, I mentioned that earlier, but the important thing is simply a base level of accreditation, something like ISO 17025. But you've got to, and quite simply, don't employ someone who doesn't have that, because they have no then internal checks on the quality of what they're doing, or not necessarily the case, but it's not been externally verified. But 17025 is probably a base level to look at. But as I said, individual countries in the Middle East have layers upon layers of local government and then national government approvals and accreditation as well. We are audited by government organisations. I'm sitting in Dubai. We're audited by Dubai Municipality as well, who will come out and watch us do stack monitoring on top of our 17025 accreditation. We are audited by NCEC and Royal Commission and places like Saudi. So there's a whole range of layers of approvals and accreditations, as I said. So, if you're out there and you want to employ a third-party lab, ask them what accreditations, what approvals they have, and make sure that those approvals are in line with what the regulator in the country that you're operating requires, because as I said, they do differ, but ask the question.
Sure. Thank you, Alex, for the detailed answer. And with the interest of time, I would say that's all for today. And now we would like to thank everyone for participating in this webinar and by being with us. So a recording of this webinar will be made available to everyone, and the web link will be shared in a couple of days. At Element, we make certain that we are making a safer tomorrow than today by testing your material, environment, and products, where our global network of experts are here to assist you with the high level of expertise. So that's the commitment from our side. And now, should you have any queries or need to access our team of experts, please use any of the contact details displayed here. Basically, these are from Middle East and Asia Pacific, but we have a huge network of technical experts sitting in different laboratories across the globe. You can find the details of our lab locations and the experts by visiting our website, www.element.com, where you can click on the location page and you can find our 200 labs, which are located in the different continent in the globe. And once you close the webinar page, a short survey will pop up on separate screen, or you will receive a survey link in your email inbox as well. So we would appreciate if you can just take 1 minute to complete that survey and provide your feedback.